Yeah, so great pleasure to have Riddhi here. Yeah, and pleasure and honor. Learn much from him. So Riddhi will be talking about large-scale geometry of randomly growing interfaces. Over to you, Riddhi.
Okay, thanks, Mohanna. Yes. Yeah, so yeah, thanks everyone for coming. I'd like to thank the organizers for the invitation and the opportunity to speak here. Unfortunately, I cannot be there in person, but I hope the conference is going very well. It's a great thing that we're moving towards some semblance of normalcy. So anyway, so I want to talk about a certain kind of randomly growing interfaces that are important in both probability and statistical physics. In particular, I want to talk about the large-scale geometry of those interfaces. So what do I mean by randomly growing interfaces? So I will specifically be concerned with interfaces in 1+1 dimension. What that means is that there'll be one space dimension and one time dimension. So the interface that we are considering is indexed by one space dimension. Typically, it will be the one-dimensional Euclidean lattice, that is Z. And at each location of Z, there will be a height function. So at each time t, each column will have a particular height, which will denote by hxt. So the interface that we are considering at time t is the top envelope of these sequence of columns. So this is the interface. So if at time t, if you plot the function hxt as a function of x, that will give you the interface. So what are the most basic examples of interface growth that one can think of? So the most basic thing would be something like the following. So you start with nothing, start with a flat line, and then at each location, you increase the height at rate 1 by some independent random amount. So each location, each column increases independently at rate 1 by some IID random amount, independent and identically distributed random amounts. So that's pretty much the most basic growth dynamics of a random interface that you can think about. It's actually quite easy to understand what happens to this random interface, because each column grows independently and the height of particular column at time t is basically sum of IID random variables. Central limit theorem tells you that the fluctuation, so the height is growing linearly in t, and around this mean, the fluctuation is of the order of square root t. And once you subtract off the mean and divide by square root t, you get a standard normal distribution. So that's the central limit theorem. So this is an example of the so-called Gaussian. And okay, so what is the important thing here is that the scaling, the square root t scaling, and the fact that the limit is Gaussian does not depend on the microscopic details of the model. It does not depend on what particular increment distribution you chose. So as long as it's IID with finite variance, the behavior, the scaling, the square root t scaling and the Gaussian limit will remain the same. So this is an example of the universal behavior, and this is in particular an example of the ubiquitous Gaussian universality class, which occurs pretty much everywhere in probability as well as in the real world. But as you can already see, this type of interfaces are very simplistic. Each column is growing independently. So many of the natural growth processes would not be covered by this type of interfaces. In particular, most of the times we'd like to model growth where the growth of one column kind of depends on the growth of nearby columns. So there are many such natural models, and those are believed to, under certain generic conditions, those are believed to be governed by a particular equation. So if h is the height function, so you look at the equation, which is del h del t depends on the second derivative of h with respect to the position vector, so del 2h del x2, plus there is a nonlinear term which is del h del x square, and then there is a this part is a random part, so this is just white noise. So if you're familiar with stochastic differential equation, this sort of equations are very common. This sort of equation should be very familiar to you. So this is what is called a stochastic partial differential equation, which was introduced by three physicists, Kardar, Parikh, and Zhang, in 1986, and now it is known as KPC equation. It's quite a famous equation both in statistical physics and in probability theory. So many naturally occurring growth models are believed to be the large time behavior of many naturally occurring interfaces, which are not in the Gaussian universality class, are believed to be covered by this KPZ equation. So I'll give you more concrete examples later, but if you are familiar with these things, so some natural examples are ballistic deposition model or corner growth model. So these are more natural examples of growing interfaces in the KPZ universality class. And how it is different from the Gaussian universality class? So one thing is important is that this is smoother, because as I said, the growth of height depends on the heights of the nearby columns, as you can see already from this equation. So what happens is that the interface here is much smoother than in the Gaussian case. So what is predicted? The predicted behavior of the interfaces in this particular universality class is that the fluctuation at time t would be of the order of t to the 1/3, and in space the correlation length would be of the order of t to the 2/3. So these are the predicted behavior of this large class of models, which are believed to be in this so-called KPZ universality class. So this is a wider class of interesting. This is believed to cover a very wide class of interesting models of random interface growth. And what happens is that it turns out that many natural, like real world phenomena, seem to experimentally conform to the predicted behavior coming from this analyzing this equation. So there are many examples. I have just listed only a few. So there's if you look at the boundary of a growing bacterial colony, that looks like, and then if you look at the lines formed when you burn paper slowly, the lines you form, they seem to have a similar behavior. And then there is this thing in physics where you look at the interface between two different dynamic scattering modes. So this is the picture where, so this also seems to, at least experimentally, they seem to conform to the particular scaling and then the limit behavior that is predicted in the KPZ universality class. And then there is some particular model where colloidal particles like coffee stains are allowed to dry, and the boundary of these dried stain drops, they also seem to conform to this particular class of models. So as you can see, because there are a lot of interesting models which seem to at least experimentally conform to this type of models, this has become a study, an area of quite interesting studies.
Quick question.
Yes.
So you said in the slide before the previous one about this TIPA 1/3, TIPA 2/3 scaling conventional.
Yes.
So but in the pictures that you are showing, there is a kind of limit. Can one? Is there some kind of empirical evidence in favor of these two conjectures? Which one?
Yes. So in some sense, the pictures you see are already scaled. So here, for example, this is so what happens is that the conjecture is that once you have scaled the vertical direction by t to the 1/3 and the horizontal direction by t to the 2/3, then it will conform. Then it will converge to some random limiting process, stochastic process. So that stochastic process kind of looks like this.
Excellent.
Yeah, go ahead. So it is indeed true that experimentally you can see the scaling of t to the 1/3 and t to the 2/3. So of course, the pictures are kind of produced after that scaling. So it looks something of an order 1. So the fluctuation in the interface looks something like an order 1 thing. Did that answer your question?
Yes, thank you. Yeah.
Okay. Right. So let me proceed. So as can be as is expected, this sort of real world phenomenon is not really something that is within our reach to analytically understand. But what one tries to do in this situation is tries to find more simplified mathematical models that retain some of the essential parts of the dynamics that gave rise to these physical examples, and tries to understand those simplified models. And there is indeed some success to that effect. And I'll talk about mostly one particular example of that kind, which is the last passage percolation model on the plane. I'll explain exactly how that is related to the randomly growing interfaces that I was talking about, but let me just first define this model. So what you do is that you take the two-dimensional Euclidean lattice, you put a random IID weight on each vertex. Now, for a reason I'll talk about later, let's just say that the distribution of the random weights on each of the edges is exponential. So it's a standard exponential distribution. Then you define something called a last passage time between two vertices. So you take two vertices. So the pairs of vertices we will consider will always be ordered, coordinate-wise ordered. So you take the vertex u and the vertex v, and you consider all the upright path that goes from u to v. You define the weight of a path simply by summing over the weights of the vertices contained in it. And then you define the statistic called last passage time by taking maximum of the weights over all paths connecting these two vertices. So that's the last passage time. And then because exponential distribution is continuous, there is a unique, almost really a unique path that attains this maximum, which we'll call the geodesic between the two vertices u and v. Okay, so now how exactly is this connected to the interface growth that I was talking about? So if you look at this picture here, so the blue region is, I have fixed some large time t, and the blue region is the region of all vertices such that they have last passage time starting from the origin is less than equal to t. And the interface I'm talking about is basically the boundary of this blue region, this deep blue curve. So this is really the interface. So as time increases, the interface grows in this direction, in the diagonal direction. So if you want to match it with the previous picture, what you should do is you should counterclockwise turn this picture by 45 degrees. Then the initial surface we start from is no longer flat, but it's a V-shaped surface. And then you using this particular last passage percolation dynamics, in time this interface grows upwards. Okay, so that's how it. So that's the, if you want to think of it as a randomly growing interface as we were talking about before, you should keep this picture in mind. So the time direction, in particular, this will be important later. The time direction is the diagonal direction like this, and the space direction is the anti-diagonal direction like this. So that's that's the way to conform to the physics terminology. So you can just study this last passage percolation model by itself, but if you want to sort of connect it to the randomly growing interface picture that I gave you before, it's useful to keep these keep this dictionary in mind. Which one is time and which one is space. So what is known about this model? So in particular, a lot of things are known about this model, which so in particular, it is known that the growth is linear. So if you go in some direction, x comma y, if you grow for some distance n, so if you go look at the last passage time from the origin to the point nx comma ny, it grows linearly, and the first order scaling by n gives you a limit which is an explicit function. In particular, it's a function square root x plus square root y whole square. That's not very important for us. But this predicted exponent 1/3 that I was talking about is actually rigorously known for this model. So in particular, you know that if you center the passage time by the first order behavior. So in particular, if you're going in the diagonal direction, if you center it by 4 times n, and then scale by n to the 1/3, then it converges to some non-trivial limit. And for those of you who were present at the earlier talk of Professor Bush, you have already seen this distribution. So this is a distribution coming from the random matrix theory called the so-called GUE trace-Wheaton distribution. This is the distribution of the largest eigenvalue of Wishart matrices, for example. And so this is the exponent 1/3 that I was talking about. And what about the exponent 2/3? The exponent 2/3 arises, as I said, that it governs the decay of correlations in the space direction, and that will show up in the transversal fluctuations of the geodesics, which I'll talk about in a couple of minutes. So just to give you a broader perspective of what this is, so remember we fixed the distribution of the vertex weights to be exponential, but this behavior is supposed to be much more general than that. It is supposed to be universal under some very mild condition. But the unfortunate reality is that even though it is believed and numerically supported by a lot of evidence that this is indeed true for a large class of weight distributions, it is known only for a very small class of weight distribution, like 3 or 4 distributions, 3 or 4 particular examples of this last class population model are actually known to be in the KPC universality class in a rigorous sense. The reason these models are exactly solvable is because there are certain remarkable bijections that lets one map these models to some other well understood objects in different areas of mathematics. So in particular, one can map this exponential last passage population to the Wishart matrices that again Professor Bush was talking about in his talk. So there are some remarkable connections across different areas of probability theory, algebraic combinatorics, representation theory, that there are some extraordinary remarkable bijections which lets these particular examples to be analyzed using some exact formula. So much of the, although we very much like to understand the universality under very general conditions, much of the literature is actually studying these exactly solvable models and trying to understand the finite details of these models using this particular, these exact formula. So what are the kind of questions of interest? Because we have this exact formula available for these models, we can actually do a lot of fine analysis of these particular models. So what are kind of the questions of interest? So basic questions of interest would be, to understand the random landscape formed by these passage times. That will let you understand this whole growth process as time increases, right? So they also are believed to have some universal scaling limit. And what turns out is that that is one kind of question that you want to understand if you want to understand this whole growth dynamics. But if you are more coming from a geometry perspective, it also makes sense to understand the geodesics itself. The structure of geodesics in any kind of geodesic space. So remember, this is not quite a metric. This is an anti-metric because of the last passage nature of the problem. So it satisfies the reverse triangle inequality rather than triangle inequality, but the geometric behavior is kind of the same. So if you are coming, if you are studying geodesic space, then it's kind of very interesting to study the structure of geodesics, structure of finite and infinite geodesics. So those are also questions of interest here. So you want to understand what is the geometry of the geodesics connecting 2 points. What are there infinite geodesics? Are there bi-infinite geodesics? So these are all kinds of questions that are of interest. And what turns out is that these 2 types of questions, although they might seem a bit different at first glance, they're actually very intricately connected. So if you have some information about the passage time behavior, you can get some information about the geometry of the geodesics using that. And if you have some understanding of the geometry of the geodesics, you can sort of feed that back into the study of the passage times and get some further refined information about the passage times. So in recent years, there has been a lot of work in sort of this understanding these 2 together. So you understand some things about the landscape itself that gives you some information about the geodesic geometry, which you again use in understanding some further finer information about the landscape. So what I want to do in the 10 minutes that I have remaining is that I'll tell you some, very briefly, I'll tell you a few results that give you the flavor of these two types of studies that have been going on. And it's a vast literature, so I cannot even scratch the surface. I'll just try to mention a few results that I have been involved in over the last few years. So as I said, so let's start with the geodesic geometry kind of thing. So what is the most basic thing that you can ask about the geometry of the geodesic, right? So you have 2 points and you have a geodesic joining them. So the first thing to ask is that how does it differ from the Euclidean geodesic? How does it differ from the straight line? So one of the measurement of that, of course, is the so-called transversal fluctuation. That you look at the maximum distance of the geodesic. So the geodesic is a random curve joining 2 points. So you look at the straight line joining the 2 points, and you look at the maximum distance between the straight line and the random geodesic. So this thing is called the transversal fluctuation. It's a very commonly studied quantity to get a handle on the geometry of the geodesic. So it was known long ago in earlier by 2000 is that this, as I said before, this 2/3 exponent of spatial correlation decay kind of this sort of crops up in the geometry of geodesic in the following way, that the transversal fluctuation is of the order of n to the 2/3 plus log law of 1. So that was already known by Johansson in 2000. A more sort of optimal quantitative estimates have been obtained in recent years. So in particular, now we know that the transversal fluctuation probability that the transversal fluctuation scaled by n to the 2/3 that is large, in particular that is larger than some large constant k, decays like e to the minus a constant times k cubed. So the upper bound was obtained by us in a couple of works, and the lower bound was obtained in this work by Alan Hammond and Saurav Sharkar in another separate paper. And in the other direction, one can also study the small ball probabilities. The probability that the transversal fluctuation is much smaller than the typical value being into the 2/3. And then in this work with my former master student Manan Bhatia, what we showed is that the small ball probability, the probability that the transversal fluctuation is less than or equal to some small constant delta times n to the 2/3, that decays like e to the minus delta to the minus 3/2. So if you're familiar with the small ball probability of Brownian motion and Brownian bridge, this type of result should seem familiar. So for Brownian motion, you get the same behavior, but instead of delta to the minus 2 here, rather than delta to the minus 3/2. So this is related to the fact that the Gaussian distribution has tail exponent into the minus x squared, whereas the Tracy-Williams distribution has upper tail exponent into the minus x to the 3/2. So that's how you get this minus 3/2 instead of minus 2. So these are kind of fine information that you can obtain about the geometry of the geodesic. And I should mention that these information are obtained by relying on the particular information about the point-to-point passage time. So I mentioned this convergence to Tracy-Williams distribution before. So there are some pre-limiting versions of those convergence results, and using those particular convergence results, you can obtain geometric information like the transversal fluctuation estimates for the geodesic. And then, there are other information that you can obtain. So for example, you can show that there cannot exist any non-trivial bi-infinite geodesics. You can also, so I guess I'm running out of time a bit, so I don't go into the details of these results, but then you can also ask, if you look at two infinite geodesics that are going off in the same direction, so semi-infinite geodesics, bi-infinite geodesics, as I said, do not exist. So what happens in a smooth Riemannian manifold is that these will, even if they're going off in the same direction, they will not coalesce. If you look at the infinite geodesics starting from a point going off in the same direction in the Euclidean space, they're just parallel lines, right? So they will never coalesce. But what happens in this random landscape is that they actually coalesce, and you can get quite precise estimates about how far they travel before they actually coalesce. So this was again, some results that we could obtain using these this kind of estimates of passage time. So now, in the last 5 minutes of my talk, I want to tell you about some different flavors of results which are obtained using this geometric understanding of the geodesic. So this is so one type of such results is the understanding the correlations of this interface. So now you go back to this randomly growing interface picture, and you want to understand what is the correlation of this. So as you look at two different time points, you want to understand what is the correlation between the surface, the interface at time t1 and the interface at time t2. So that's naturally a very interesting question. So one can formulate this question in quite a general setting, actually. So, so far we haven't talked about the, the importance of different initial conditions. So we only defined this randomly growing interface starting from this V initial condition, which is also commonly referred to as the step initial condition or the droplet initial condition. But instead of the V initial condition, you can put any kind of general shape to start with. So how would that work? So at time t equal to, so remember time 0 corresponds to this anti-diagonal line x plus y equal to 0. So you just put some random function on that line and you calculate your last passage time by adding the value. So you start from any point on that line at time 0, you go to your destination vertex, you pick up some last passage time and then you add the initial value to it. Then you maximize over all possible starting points. So that's what is known as a last passage population model with the particular given initial condition pi. Then, as I said, the question of interest here is to understand the covariance or the correlation between the interface started from the initial condition pi at time n versus at time r. When n and r both become large and then r over n is a fixed constant or something like that. So as I said, there are a number of special initial conditions. In particular, this V-shaped initial condition, you can see that corresponds to this particular choice of function pi. So this is known as the droplet initial condition. And then there is also the thing called flat initial condition, which is exactly the same as starting with a flat surface rather than this V-shaped surface. So this corresponds to the choice of the function pi identically be equal to 0. So there also, the first order behavior and the scaling remains the same, but the scaling limit is somewhat different. So instead of the GUE Tresividum distribution, it converges to what is known as the GOE Tresividum distribution. But the scaling remains the same. So one of the results that we could obtain about this, the decay of correlation of this interface with different initial conditions using the understanding of the geometry of the geodesics was the following. So the natural scaling, so if you look at the quantity Tn, it has natural scaling of the order of n to the 2/3. Natural scaling of variance is of the order of n to the 2/3. So when n and r are comparable, so the natural thing to look at would be the covariance scaled by n to the minus 2/3. So what we could show is that when r over n is tau, so r over n is so r and n are comparable and the ratio is tau. So it's hard to obtain an exact formula for the covariance for all values of tau. So one studies kind of two asymptotic directions, tau going to 0 and tau going to 1, where it's possible to get more precise information. So one actually has both kinds of results, but here I have only listed the small tau result. So for droplet initial condition, one can show that the scaled covariance kind of grows or like decays like tau to the 2/3 as tau goes to 0. Whereas for the flat initial condition, the exponent changes. The exponent becomes tau to the 4/3 rather than tau to the 2/3. So again, it's hard to appreciate these results without me explaining anything more about how these are obtained. But what I want to emphasize is that this is not so the work that goes into the proof of this result is quite critically connected to the understanding of the geometry of the geodesics. So on the surface, this question of covariances has nothing to do with the geodesics. It's just a question about the joint distribution of the passage times. But to actually answer this question, one has to use the understanding of the geometry of the geodesics that kind of went into the previous results that I explained, and then use that to get this more refined information about the joint distribution of the geodesics. So this is a very interesting interplay between these two types of results, which I wanted to point out. So I'm yeah, I probably should finish soon. Just summarizing that it's an important topic. This KPC universality, which is mathematically challenging to understand. The question of universality is particularly challenging to understand. But there are some canonical exactly solvable models for which people can get a lot of information. And so there are these two types of questions about geometry of geodesics and the geometry of the landscape of passage times, which understanding of one kind of fits into the understanding of other, which is quite interesting. Yeah, I think I should just stop here. And thanks very much for your attention, and happy to take questions.
Thank you very much, Riddhi. Lovely talk. There are a bunch of questions. So first, Vidhi has a couple of questions and Manju has a question. So
yes.
May I request, can you unmute?
Hello. Can you hear me?
Yeah, Manju, go ahead.
No, I had,
yes.
The question that I posted in chat was about the pictures. You showed some experiments. Were those 1+1 dimensional experiments or?
Yes. So these are actually 1+1 dimensional experiments.
I see.
So these are, so there are actually experiments in higher dimensions also, but the higher dimension, in 2+1 dimension, what the answer should be is not clear at all. So in 1+1 dimension, you can do some renormalization group analysis to predict this 1/3 and 2/3, and then you can match it up with the experimental results. So in 2+1 dimensions, there are experimental, there are experiments and there are some numerical values, but there is no sort of theoretical prediction because somehow the renormalization group, I don't understand very well why it doesn't work, but this renormalization group analysis does not seem to work in the 2+1 dimension. I mean, at least it seems like in 1+1 dimension there is sort of a unique fixed point which gives you this particular 1/3 and 2/3, but in 2+1 dimension there seems to be a lot of different possible scalings, and there isn't any consensus among physicists even what this would be. So the pictures I showed are actually 1+1 dimensional.
Okay. I had one more. So you showed this distance from the diagonal, right? That you had results on the tail end or the lower end, both. So distance of the geodesic. So is the weak convergence there, or distance divided by into the 2/3?
Yes, so it converges weakly to some stochastic process which is not Brownian, which has a Holder 2/3 minus. So not much is known about the limit, but there is that it converges in C01 to a stochastic process, a continuous stochastic process.
Which process are you talking about? I was talking about a random variable, the distance of the maximum distance of the geodesic.
So I am talking about, so you can look at the distance as a function of the time, right?
Okay. Oh, I see that.
Of course, the maximum also converges to.
I see. Okay. Great.
So this is so there is a convergence result known at the level of the process. So you can get a convergence result at the level of the maximum also.
Okay. Thanks.
Yes.
Just I had one question. That n to the power of 1/3, exponent 1/3, is there any intuitive explanation for that? Number one. And secondly, I was also asking about this thing. In the KPZ equation, if you take z equal to 0, it is a non-linear differential equation. Does one know the solutions?
So the non-linearity is exactly the problem. So it's not. I think it's so. What happens is that it becomes ill-posed. So I think what you can do is you can take a log of this.
No. go back to the KPCD equation and then take xi to be 0, then it is a deterministic
Yes.
PDE, but which is non-linear. Does one know the solution?
Yes. So this is, I'm not 100% sure about it, but I don't think a solution should probably not exist in the classical sense.
Aha, I see. Okay.
So it will, I mean, so you should probably have to define some sort of a weak solution. So this nonlinearity will create some sort of a problem, which is exactly also the situation. What happens, why rigorously defining the solution of the KPC equation requires this heavy machinery of hierarchy regularity structures. The reason is that this nonlinear term will blow up.
Yeah.
So I'm not entirely sure what will happen if you just make it non-random, but I think the problem will still be there. So you will have to define some sort of a weak solution or an energy solution.
I see.
So I'm not entirely sure about the PD aspect. So I
Yeah. And the other thing is about 1/3 exponent. Is there any intuitive explanation?
Yes. So there is an intuitive explanation actually that one can give. Is that so? Let me. You still see my screen, right?
Yeah. I can see. Yeah. Oh, yeah.
Okay. So look at this particular formula. So there is this limiting behavior, which is the square root x plus square root y whole square.
Right.
So what is it? So locally, if you look at it, so if you look at the particular direction 1, 1 and you expand this function around it, so you have the first value 4, and then in the space direction, there is a negative parabolic decay.
Right.
So what you have is that your deterministic function, that the first order deterministic behavior is something like minus a parabola, a constant minus a parabola.
Right. Yeah.
So what you can think about intuitively is that there is this parabola which is a deterministic function, and on top of it there is a randomness.
Right.
Okay, so now if you are very naive and you just model this randomness as a Brownian motion. So if you just look at the function, so if you scale things properly, you will see that the right scaling for this Brownian motion would give you something like, which is Brownian. So if you are trying to model this as a Brownian motion minus a parabola, it becomes Brownian of x minus x squared over t. Yeah, so because this decay also depends on t, so the correct scaling, if you just expand, if you do a Taylor expansion of this first order behavior, so you will see that this becomes b of x minus x squared over t.
I see. Yeah.
Now you want to understand, so toy model is, you want to understand what is the maximum of a Brownian motion b of x minus x squared over t. Now b of x is like square root x.
Right.
So the maximum will be achieved if when square root x is comparable to x squared over t.
Okay.
So that gives you x equal to, that gives you the 1/3 fluctuation.
Oh, thank you.
So that is the intuitive explanation for 1/3. That's so essentially, so the behavior is expected whenever you have locally Brownian fluctuation around a parabolic curvature constraint. So that's what physicists say, that KPC behavior will arise whenever there is a locally Brownian behavior together with a global parabolic curvature. So that's one of the intuitive explanations that's the best intuitive explanation that I know.
Yeah.
Okay.
Okay.
Any questions from the audience here? Yes, go ahead.
Hello.
Yes.
This is question related to deterministic form of KPZ equation.
Yes.
That means when the noise is zero, because there is a quadratic nonlinearity,
Yes.
I can think of there will be local existence of solution for a small group. And if you want to continue with the direction time, then you need some bound. But I don't see how some bounds can come. I mean, you can perhaps get some bound for you, but you may be needing a bound for UX is L2 or something of that kind. That seems to be quite hard because you get a nonlinearity fx square. I mean, the partial derivative of a with respect to x, the square of that. So, do you have any reference or
So you mean the solution of the solution of the deterministic KPZ equation?
yes?
So actually, no. Unfortunately, I'm not very familiar with the PD aspect of the literature, so I cannot give you anything completed at this point. Yeah, sorry about that.
Yeah. Thank you.
Not something I'm super familiar with. Yeah, it's a hard. I mean, the PD questions are hard because of the nonlinearity. That's
Question.
what.
Sorry.
Yes.
Because of the noise, and some noise, you are getting some interesting result. Because I am not a man from stochastic method or stochastic method.
Yeah. So what I can tell you is that how I mean I can tell you briefly how one solves in what sense one solves the KPZ equation with the noise. So it's a regularization procedure. You know, this the same regularization procedure that you do with usual PDs. But what happens is that if you do the standard regularization procedure, the solution will become unbounded. So, you know, you regularize with some parameter epsilon and then you send epsilon to 0. Then the solution becomes unbounded. So what was the theory of hierarchy? You know, this graph path theory and this regularity structure theory, what they do is that you do the regularization. So you make H into H epsilon by convolving with some smooth kernel. And then there is something called a renormalization counter term. So to make sense of the regularized equation, you can't just let H become H epsilon. You also have to subtract off epsilon to the some minus large power. So there is a particular choice of this renormalization counter term that when you add to this renormalized equation and then you solve the renormalized equation and take appropriate limit as epsilon goes to 0, the limit converges in an appropriate topology. So that's what happens in the version where you actually have the white noise. So if you actually make the noise equal to 0, what kind of effect that has this on this of regularization is not something I'm completely sure about. So the usual method of solving this equation is so there are two ways of solving the KPZ equation. One is that instead of solving for H, you solve for e power H. So e power H will be a solution of the stochastic heat equation. So the nonlinearity will go away. So it will just be a heat equation plus plus a noise term, a multiplicative noise term. So that one you can actually solve using the usual procedures, using usual regularization procedures. And then you can simply say that the solution of the KPZ equation is log of that solution. But then it will not be a random variable, it will be a random distribution. So in some sense, so the work of Martin Heider and others was to show that the solution you get from this log transformation is actually the same as the solution you get from this using these renormalization and the regularization procedure. So in some sense, that is the right solution of the KPZ equation. So, I mean, there probably is some corresponding theory of the deterministic case. I'm just not very familiar with it. what exactly happens if you just set the noise to be equal to 0.
Okay, thank you.
Yeah, so Riddhi, just a couple of clarifications.
Sorry, again, can you please repeat?
No, I'm asking basically just for a couple of clarifications on what you were saying. So you said something about this joint behavior of families of last passage times versus
Yes.
the geometry of y geodesics. So,
Yes.
so is the connection via one functions or something like that, or what exactly? Yeah, I mean, where does the
So connection by what function are you saying?
Buseman functions? No?
So Buseman function, yes. So Buseman function is one way to do the connection. So Buseman function, of course. So one way to study the connection or establish the connection is indeed via Buseman function, but that is not the only way. So one can actually make this connection by some other transformation also. Like, so there's something called Heatman transformation in probability.
Yeah.
So you can also make the connection via that sort of transformation. So Buseman function is indeed a way to make that connection, but it is not the only one.
Okay. Thank you. The other thing is that you had said something about the distance to coalescence having this exponent, right?
Yes.
Yeah. So this was also for integrable models, or this is in the collection of are these for exactly solvable models also, or?
Yes. So you know, all these results that I mentioned are believed to be true for all these general last passage population models without any exact solvability. But as of now, we are able to show these things only for exactly solvable models.
Okay, so yeah, so which is quite okay. So I wanted to ask about exactly that. So is there some kind of a test case distribution which is supposed to be, I mean, a test case for the universality? I mean, beyond exactly solvable models. I mean, there could be sort of perturbative things around the exact solvable models, but are there sort of test cases which are supposed to indicate the universality class and distributions which are supposed to indicate the universality class?
So yes, so the problem, I mean, the answer is no actually. So the problem is that these exact solvable nature of these models are actually very fragile. So any kind of perturbation you do kind of destroys the integrability completely. So, you know, unlike in the random matrix cases, so if you are familiar with the history of the understanding of universality in random matrices, people first understood the Gaussian matrices, you know, where you could write down the exact joint distribution, and then you could understand perturbations of Gaussian matrices. Unlike that scenario, here what happens is that there are these exactly solvable models, which are like islands in the huge sea of all possible models, and then once you just perturb slightly, just move slightly outside of this few exactly solvable situation, the whole structure on which the theory of exactly solvable models is built is completely destroyed. So there isn't any particular kind of nice examples which is not quite exactly solvable but retains some of the features of the exactly solvable models for which you can hope to get something out of it. So no, of course, one cannot say that something is not exactly solvable because you know there might be some exact formula which will be found in 20 years time. But these so far nothing is known in that direction.
So just one last question before we finish. So in the last bunch of slides that you have presented, essentially about different initial conditions and giving different exponents. One was to that,
Yes.
right?
Yes.
So are there also universality classes of initial conditions, which are
Yes. Yes. So this is something, you know, this is something that is again, you know, I mean, this is so. Well, this is not something that is worked out anywhere, but it is believed to be true. So, for example, you know, the flat. Um, so, so any initial condition that has fluctuation subdiffusive should give you the same exponent as the flat initial condition, and any initial condition that is sufficiently curved, that it might not be exactly a V-shaped initial condition, but it looks curved enough, then it should give rise to the same exponent as the droplet initial condition. So there are indeed exponents. These exponents are, so there are universal classes of, believed to be universal classes of different initial conditions, but this is not something that is that exists in the literature as it is. But yeah, this is something that is definitely believed to
exist. Thank you so much. This is wonderful. Yeah. So yeah, thank you very much.
Thanks very much.